Okay, let's move on to the next problem. How are we doing on time? Not too bad. Okay, now I'm going to ask you next part of this. I'm going to ask you. You repeat this study in Brooklyn in 16 pubs and find a mean of 34 beers and a standard deviation of 7.1. Calculate the confidence interval for the mean number of beers served in Brooklyn pubs. I'm not going to go through that whole calculation right now, but I'm going to ask you for the standard error is going to be, we don't have the population standard deviation. We have to use the sample standard deviation, which is 7.1. The sample size is 16, so we're going to divide 7.1 by square root of 16, or 4. So that's going to come out to be about 1.7 or something like that. So 1.75. So our standard error is 1.75. So when I'm calculating my margin of error, am I going to use 1.96 in this situation? Opinion? No, I'm going to use the t-score that represents how many degrees of freedom? Okay, let's look up what it is. Let's see where it is here. I keep losing stuff here. I'll reopen it. There it is. Okay, so 16, sample size 16, 15 degrees of freedom, and for 95% confidence interval is going to be 2.13. Right? It's going to make a significant difference. It's going to be like about 6-7% difference in each direction for a confidence interval. Okay, now let's just take a quick look at this again. This column represents what we need for a 95% confidence interval. Most of the time, we're going to be doing two-sided tests. In other words, we're going to want to know what the low end of our confidence interval is, what the high end of our confidence interval is. That's basically a kind of a two-sided test. When we compare things later on, we may compare one group's mean to another group's mean. But going in ahead of time, we may not know whether one group is higher than the other before we actually do a study. So we start off with the assumption that that these two groups, one could be higher, one could be lower than the other group. Okay, so when we do a two-tailed test, when we're willing to accept 5% chance of error, in other words, have 95% confidence that we're right, okay, we're really saying that we're willing to have a tail on either side that represents 2.5%. Half of our 5% chance of error is on the upper end, half of it is on the bottom end. Okay, so often on these tables, you may not see confidence level 95%. You may see T alpha is equal to two-tailed alpha is equal to 0.025, or right tail probability for T is 0.025, or left tail probability is 0.025. So if you're only talking about one tail at a time and you want a two-tailed test, which is mostly what we do, you're looking at this particular column. So naturally, if you got a 90% confidence interval, what is each tail going to represent in terms of error? 5% on one side, good work. 5% on the other side. And a 99% confidence interval is going to be 0.5% on one side and 0.5% on the other. And most of these other intervals you probably will never bump heads with. Okay, so I'm going to move on to the next problem. Okay. A secret undercover Department of Mental Health and Hygiene, Department of Health and Mental Hygiene study of randomly selected restaurants on St. Patrick's Day finds that the number of slices of corned beef on the lunch specials were as follows. The sample size is 20, I think, right? About 20. Is it 20? No, it's not. How much is it? 16. Sample size of 16. First of all, what are our assumptions here? Randomly selected, normal distribution, right, and so on and so forth. Okay. Calculate the mean number of loads let's see. Oh, I forgot to change some of the words in here. I changed the problems. I forgot to change the words. So I'm gonna calculate what my mean is for my sample, and I'm going to calculate my standard error and my confidence interval. Okay, so now let me just go over here to Excel, and I think I actually created an Excel file that's on Blackboard that contains this information. and it's called corned beef dot xlsx. Okay, so here's a sample. It's got 16 restaurants that have been randomly selected. One of them over here, the real cheap one over here, you 4 slices of corned beef. Real good one here is 15 slices of corned beef, and so on and so forth. So I'm going to find what the mean is for this group. Okay, so it's going to be the average. Okay, I'm going to find the average for this entire group. It's about 10 slices. The standard deviation is equal to 3.1. The standard error, okay, unfortunately Excel that I can find, that I've ever been able to find, doesn't have, unless you load in an add-on pack, doesn't have a direct calculation for standard error for some reason. You think it would, but none that I've been able to find. If you find it, let me know. Okay, is equal to the standard deviation divided by the square root of the sample size. I'm about to make this bigger because, to tell you the truth, I can barely see it. There we go. Okay, there's my standard. There's my mean x bar, right? There's my standard deviation. There's my standard error. Okay, now I'm going to calculate my confidence interval. It's going to be equal to 10.62 minus. Now, what am I going to use for this? 1.96. What's the sample size? 16. How many degrees of freedom? 15. So on the t-table, what was that? What was that again? Anybody remember? 2.13? 2.13, that sounds right. Times my standard error, which is 0.78. Enter. Okay, equals, again, x bar plus 2.13 times my standard error. So my confidence interval is 8.4 to 11.7 slices of corned beef. That's what I think the true population mean if I had gone to every pub in New York City would be on St. Patrick's Day. Okay, so now that's one question I asked. But then the next question I asked was, let's say that somebody did an exhaustive survey of all of the pubs in Boston, every pub in Boston. And they know that for the entire population, that on average you get 12 slices of corned beef. Can we say with 95% certainty that you get more corned beef in Boston than you do in New York? What is Boston? Boston is 12 slices, right? And New York, do we know what the mean is? Do we know what the true mean is in New York? No, we don't. Our best guess is that the true mean is somewhere between 8.4 and 11.8, 11.7. So we're 95% sure it's in that range. So that means we're also 95% sure that they're getting more corned beef in Boston than we're getting here. Right? We're going to start applying logic like that to real public health situations. We're going to be trying to predict whether or not one group is different from some known value or for some value, some average for another group. And that's what this is all about. I mean, for instance, when in medicine, when you test a drug, you want to know whether the the reduction in blood pressure is greater for the control group, or for the placebo group, or for the drug group, right? And how are you going to know that? You know, because some people's blood pressure is going to go up, some people's is going to go down. On the average, there's going to be some change between those two groups. You're going to want to know if certain kinds of intercessions are going to have a benefit health-wise, right? And whether or not they're worth spending money on. You're going to want to know whether this pilot study, which took 30 kids and put them in a reading program, and at the end of the reading program, were they reading at a higher level than matched up classmates in another group that didn't take this reading program, and was it worth spending the money to see and seeing whether or not they actually improved, or whether the improvement was, maybe they had a little bit of an improvement and wound up not being big enough for you to be able to tell that it was not due to chance. Okay, so we're going to be applying this in real life situations. And in fact, you're going to be doing that probably for the rest of your career, is applying this kind of stuff in those kind of situations. Okay, so now, no. I think you will occasionally. At least you'll be reading other people applying it. If you're not applying it yourself, you'll be reading the results of other people applying it. Okay, so I mean, the corned beef thing is just like to add a little levity to the whole thing. So now, yeah, you're getting hungry, right? We have beer now. Tell me that when this class is over, you're not going out for a beer and some corned beef. Right? Okay, so anyway, I'm gonna take this Excel spreadsheet now, and I'm going to import it into SPSS. Okay, so I'm going to go through the exercise now of actually importing it. Okay, so now, if you don't want to import it, I uploaded the same file as an SPSS file, but I just want, a couple of people have asked me about how to import an Excel file into SPSS. So I'm going to open SPSS. Actually, I kind of have it open. I just need to get it to appear. And I'm going to go up to File. I'm going to say Open, Data. Now, I can navigate around. I can use this browsing window to navigate around my computer to find. I want to get some stuff out of the way here. And I also just want to glance over here. I'm sorry, Catherine. I'm not. You're going to have to type in what you'd like me to repeat. Okay. So I'm going to navigate over here to the folder where I have that Excel spreadsheet, which was here. And you'll notice the only thing that's highlighted that I can actually click on right now is that SPSS file called cornedbeef.sav, which if you are not interested in importing it from Excel, that you could just go ahead and say open, and that would open up. But I'm interested in importing the Excel file. So I don't see the Excel file. I can see the Excel file, but I can't open it. If you go down here and look at the format that SPSS is looking for when it's doing this browsing, it's only looking for .sav files, SPSS data files. If I click on that, I can change that and tell it to look for Excel data files, right? And in fact, then all of a sudden that one, the Excel data file becomes highlighted, so I can pick it and then say, go ahead and open that file in SPSS. When it does open that file, it first tells me it sees data between A1 and A17. That's 16 numbers. It says it's 17, it sees data in 17 cells. What's in the 17th cell? Anybody notice? There was a word in there. What was that word? Corned beef, right? There was a word corned beef, and at the top of the list of numbers, I wrote corned_beef. I put the underscore in there because SPSS doesn't like spaces in its variable names, right? So I put that. I knew to put that underscore in there or leave the space out. So it sees basically in that Excel file, and you have to know this ahead of time. It sees the variable name in the first spot, and then below it's 16 numbers, right? So you'll notice a little tick box over here. Read variable name from the first row of data. That needs to be clicked for this situation because otherwise it'll try and read that what's in that box is data, and it's not data, it's the variable name. If I don't have a variable name at the head of that column, I have to unclick this because if I don't unclick it, it will ignore that top line or try to use it as a variable name instead of including it in the data, and I'll lose one of my people in my data set. In this case, I'm going to leave it clicked. You guys got why I'm leaving it clicked? Okay, I'm going to click OK. It's going ahead and importing this data file. Okay, and if you'll notice, I can't blow this up for some reason. You would think $1,000 piece of software, or our silly version of this, our scaled down version of this $1,000 piece of software would do this kind of stuff for you. But what are you going to do? So at any rate, I'm going to bring this towards the center. Maybe that'll make things a little easier. So here you see it. It's imported all of these different numbers, and it put at the top there. It put slices is what I had at the top. Right? So it put that at the top. They used 10 slices, 14, 7, and so on and so forth. If I click on variable view, you'll see there's one line filled in for the variable name slices. If I want, I can make a more descriptive label such as number of corned beef slices. Okay, and so on and so forth. And I can tell it, by the way, this is not nominal data, this is numerical data. I'm going to change it to scalar. Okay, sometimes it reads it correctly, sometimes it reads it incorrectly, but this variable view, which I can click on back and forth, this variable view describes what kind of variable that we're working with and the various rules about how many decimal places it has and so on and so forth. Even how it's displayed, is it centered, so on and so forth. So I'm going to go back to my data view just so I can see it. And I'm going to repeat this calculation that we just did for the confidence interval using SPSS. Okay, so I'm going to go up here to Analyze. I'm going to go to, well, Descriptive Statistics. I'm going to try that first. I'm going to go to, let's see, Explore, because that usually tells me the most. Explore, I'm going to move a number of corned beef slices, the variable, into the dependence list. There's no factor list because it doesn't separate out into corned beef on rye and corned beef on whole wheat and so on and so forth. So I could have put that variable in there, right? So I'll click OK. Maybe I will next time. If we ever happen to have this class again on St. Patrick's Day. Okay, so let's take a look at what we have. The mean is 10.06, same thing we found in Excel. The standard deviation is 3.13, same thing we found before. The standard error is 0.782, same thing we found before. And here is the confidence interval. And you will notice something interesting about this confidence interval. This confidence interval, I don't know if can I get to the one that I did before? This confidence interval is always based on the t-table. It's never based on just using 1.16. It doesn't matter if the sample size is 16, like it is in this case. It'll use 2.13, the same as we did. If the sample size is 999, it will calculate a precise t-score that you need for that particular number of degrees of freedom. So it doesn't care. It does all the work every time. It doesn't take any shortcuts. So this is our 95% confidence interval. And you can see it's basically the same thing that we had before. Now, I'm going to do this one more time. And I'm going to do our analysis where we compared the number of slices that we got in New York, the sample that we got in New York, to a known population in Boston. And that's called, since we're using t-scores for this, it's a sample. We're trying to figure out how likely, where the mean is, what the range we can assume the mean is, and we're comparing one mean to another mean very frequently. In this case, we're comparing our sample mean to a known quantity, a known population, which is Boston, which is 12 slices. So I'm going to go, instead I'm going to analyze, and up to now we've gone to descriptive statistics, frequencies to do simple counts. We've gone to descriptives to do some simple like mean and standard deviation. We've gone to explore to get a bit more out of it and so on and so forth, and also to factor it into male and female and so on and so forth when it's appropriate. This time I'm going to slide down to the next one beyond descriptive statistics to compare means. We're going to compare the mean of our sample to the mean of the population in Boston. Well, I got a bunch of choices when I do that. One sample, notice it calls it a t-test. It's looking at the comparison of samples, not populations. If it knew the populations, if that were possible, it would be doing z-tests, right? It's doing t-tests. Okay, it's looking for one sample t-test, independent samples t-test. That says to me more than one sample, right? Independent samples. Paired samples t-test. That sounds like a special version of t-test, right? And a couple of other selections here. We're looking at a one sample t-test. We only have one sample. We're comparing it to a known mean. And sure enough, the window that comes up asks me, what's the test variable? I'm going to say, yeah, it is. It's a number of slices in New York. And what's the test value? What are you comparing that to? I'm comparing that to a known mean for Boston of 12. And I'm going to ask it, I'm going to say, okay, go ahead and solve this for me. And it does what's called a t-test. It actually calculates the t-value. How far away? What was the mean that we decided that we had for New York? It was roughly 10.06. What was it, 11? 10? It was 10. For New York, we thought the mean was approximately 10.1 slices. Okay? instead of just looking at a 99%, 95% confidence interval and saying, oh, it's outside of that confidence interval, which we just did with Excel. Instead of just looking at that, SPSS takes it one step further. It says, hey, listen, I can do a lot more than tell you that they're different. You're 95% sure that they're different. I can tell you how likely it is more precisely that they're different. And how can it tell you that? Well, it takes your mean that you got for your sample, which was 10.1, and it looks at Boston, which is 12, and it says, how many standard errors apart are these two for this sample size? How far apart is 10.1 and 12? Is it, if it were exactly 95% confidence interval, if we're right at the edge of the 95% confidence interval, we know it would have been 2.13 standard errors apart because that's the only one we calculated it for, the 95% confidence interval. But it tells us, in fact, that they are 2.476 standard deviations, standard errors apart from each other, those two numbers. And it says, well, in my chart for 15 degrees of freedom, that will only occur if your two-tailed significance, if your p-value, your probability of being wrong, if you say that they're the same, if you say that they're different, is 0.26%. Now, this is a two-tailed test. See, it says significance two-tailed. When it says 0.26, how much is in the lower end? How much is in the upper end? 0.013 is in the lower end, 0.013 is in the upper end. So not only can we say that Boston is different than New York with 95% certainty, right, because of our confidence interval, we go a step further with the t-test. We can say that there is 2.6% chance of being wrong if we say that these two cities have different amounts of corned beef in their lunches. Right? If we say that they're different, there's only a 2.6% chance of being wrong. Okay, so now if I'm going to use SPSS this way in the future, I want to set a limit. I said to myself, instead of looking at it now in terms of how confident that can I be that I know what the real mean is, right? What's the range? Now I'm looking at, what if I say that they're different? What if I say they're same? And now I want to reject that and say that they're different. Okay, I start with the assumption that they're the same. And I want to do this test and now be able to say that they're different. If I go ahead and say they're different, what are my odds of being wrong when I do that? In this case, the odds of being wrong are 2.6%. No, that's exactly what we just said. I just repeated it. Okay. So now I tend to repeat myself a lot. So at any rate, so now you got that, right? So in general, let's think about this. If in general we're happy with 95% confidence intervals, what do you think is the level of error that we're willing to accept in most studies? We're willing to be 95% confident, so we're willing to be wrong what percentage of the time? 5% of the time. Unless occasionally, if we want to be 99% confident, we're willing to be wrong 1% of the time. In other words, it's another way of saying we're willing to be wrong 1% of the time. Okay, so now, what is that error, that level of error that we're willing to be wrong called? Yes, the significance, they call it the significance. In class, we gave it a letter name. It's a p-value, right? Significance, same thing as the p-value, is the same thing as, the p-value and the significance are the exact level of error. What's the number at which we say that if we can get under that chance of being wrong, we're happy to say that they're different? Alpha, that's your alpha error. Beta error is something different. We'll get into that later on in the semester. Our alpha error is 0.05% if we're willing to be 95% sure we're right, if we say that they're different, and willing to accept a 5% chance of being wrong if we say that they're different. Why don't we just want to be like 100% sure that we're right? What? Not possible unless we know the population, unless we're willing to do the entire populations, right? So we pick a practical limit. Most of the time that practical limit is 95%. So we use an alpha of 0.05. Sometimes we want to be, it's more important that we be right. So we might choose an alpha of 1%, right? So in this case, if I told you that our acceptable alpha error was 0.05, would we reject the idea that these two things are, that you get the same amount of corned beef in New York and Boston? Would we go ahead and say they're different at this point? Yeah, we would, because our significance or our p-value was less than 0.05. We have less than 0.05 chance of being wrong. What if I told you that alpha was 1%? Would we say that Boston and New York are different then? No, we wouldn't, because our significance is different, right? Is bigger than our alpha error is. In other words, we have a bigger than our acceptable level of being wrong is in this particular study. Okay, so that's how we're going to be working with that from now on. So the last problem, okay, is, let's take a look at the last problem. Okay, okay, so now this is going to go on, this is looking a little bit different. Okay, we're graduating now to real hypothesis testing. Okay, a fellow student says the average salary of graduates in your major is $40,000 per year. You don't think that this is correct. You think that the average, I'm going to change this. You think that the average salary is different than this. Anybody have any idea why I just changed that to different? Because it could be wrong in each direction. It could be less or it could be greater. If I had left that, you thought it was higher only, could only be higher, this would be something that you would call a one-sided test. And all 5% chance of being wrong, you would put on one side of the distribution, right? I don't want to get into that now. We'll get into that later on. We don't need that today, okay? So I'm going to say it's different. To show your fellow students, he's wrong, you simply take a simple random sample of 100 graduates from the last 5 years and ask for the amount of their starting salary. You find that the sample mean is 31,000 and the sample standard deviation is 4,000. Is there evidence to support your claim that the population mean starting salary is different than 30,000? Okay, what are our assumptions here? Normal distribution, randomly sampled, so on and so forth. Okay, so now I'm going to put together two hypotheses. One of them is our null hypothesis, meaning that I don't think there's any difference. My hypothesis is that there's no difference between these two groups, between what we think it is and what it really is. So what would our null hypothesis be? Our null hypothesis is that the average salary is what? Is equal to 30,000, right? That's what we're starting with. 40,000. Okay, that's our null hypothesis. Now, I'm going to make up an alternative hypothesis. What's my alternative hypothesis going to be? It can only be one thing. If the hypothesis is the average salary is equal to 40,000, my alternative hypothesis is that the average salary is what? Is not equal to 40,000. Okay? Almost universally, your null hypothesis is going to be that there's no difference. Average salary is equal to 40,000. This is a single sample hypothesis, right? I'm just pointing at a number, just like our Boston, New York hypothesis would have been that New York New York slices are equal to the same as Boston, or 12 is equal to New York average number of slices equals Boston average number of slices, or New York slices equal to 12, or Boston slices is equal to 10.1. Any one of those things, right? There's no difference between the two groups, or between the number you pick and what you're testing. Your alternative is that there is a difference, that Boston is different than New York, that the salaries, the average salary of the population from which those 100 people are drawn is different than 40,000. Was it 40,000? Yeah. Okay, yeah, it was 40,000. Okay, all right. So now we're going to calculate our test statistic. Okay, so now our test statistic is going to be how far away from the estimate that the value of the parameter is specified in null hypothesis in terms of standard error. So what's our standard error here? What would be our standard error here? Do we have an idea of what the standard deviation of either of these populations is? No, we don't, but we have the standard deviation of the sample. Okay, so that standard deviation is 4,000. So standard deviation equals 4,000. Okay, so now standard deviation, the standard error is going to be equal to my approximation of the population standard deviation, which is 4,000, divided by the square root of the sample size, right, which is 10, which is 100. Okay, so that's going to be 400. That's going to be my standard error. Okay, so now there's a couple of ways I could take a look at this. Now, one way is to calculate a 95% confidence interval for my sample. What was my sample? My sample mean was 31,000, right? So what's my confidence interval going to be? My confidence interval is going to be equal to 31,000, right? Plus or minus, what am I going to use here for my z-score or my t-score? Well, sample size is 100, so I'm going to use my z-score, which is 1.96. If it were a smaller sample size, I would use the appropriate t-score if it's under 30. Okay, 1.96 times 400. So my confidence interval is going to be, okay, and I assume I'm right on this, it's going to be, say, roughly 30,000 to 32,000. So I'm 95% certain that the real mean for this population that the 100 graduates were drawn from had an average starting salary of between 30,000 and 32,000. Now, what was my original null hypothesis? That the average salary is 40,000. Can I say with 95% certainty, or in other words, less than 5% chance of being wrong, that the null hypothesis is false, right? And that the alternative hypothesis is true? Can I? Yeah, I can, because it's outside of that confidence interval, right? So what is that called? What I just did was I rejected my null hypothesis and I accepted my alternative hypothesis. That's what the name of this whole game is. You establish a hypothesis says that there's no difference between group A and group B. Then you establish an alternative hypothesis. There is a difference. In some cases, 99% of the time, it's going to be that you're just looking for a difference. Occasionally, 1% of the time, it may be that you understand that it can only be higher or lower the other group. So you make it a one-sided test, but you rarely do that. You don't do that very often. But the deal is that in order to reject that null hypothesis, you got to be at least 95% certain that you can do it. Or in other words, you want to be at least 95% certain that if you reject it and accept your alternative hypothesis, you have less than a 5% chance of being wrong. Now, you may have noticed here that we predicted we could reject our null hypothesis by using the confidence interval. It didn't tell us. All we know is that there's less than 5% chance of being wrong. It didn't tell us precisely what the odds are of being wrong, right? Just like with SPSS, we're interested in that, aren't we? So now let's take another look at this. Now, how do I know what the odds of being wrong are? Well, we could take, actually, I can take either one of these means. I can say to myself, remember X bar minus the mean over the standard deviation, right? That'll give us a z-score, right? Okay, so I'm going to go ahead and do that. I'm going to say X bar is 40,000, right? Minus 31,000. It's going to come out to a ridiculous number. I'm going to change this. I'm going to change this to 38. Okay, and my confidence interval is going to be, confidence interval is 38, 37 to 39, roughly, to 39,000. Right? We can still reject the null hypothesis because it's outside of the confidence interval. Okay, so I'm going to say 40,000 minus 38,000, right? Right, over my standard deviation, which was, how much was my standard deviation? Oh, I'm sorry. I'm sorry I did that now. Why am I sorry I did that? No, I'm not sorry I did that. Let me think about this for a second. Yeah, I can do that. Okay, yes, my standard error rather. So my standard error is 400. Okay, so what is that equal to? What's our z-score? Our z-score is equal to 2.5. Okay, now, how big a difference, how far down on the distribution do you have to be to get a z-score of 2.5? Well, one way I could do this is to get my z-table out. And I can see that 2.50 is 99.4% of the curve is below that. So that leaves 0.6% of the curve in that upper tail, right? So what's my p-value? This is a little tricky. What's my p-value now? Is it 0.6%? What kind of test is this? How many tails? 2, right? So I got 0.6%, but I got to remember that it could just easily been lower, that the salary could have been lower. So it's 0.6 and 0.6. So my p-value is 1.2%. It's double what the tail turns out to be. Okay, so if my acceptable level of error is 5%, I reject my null hypothesis. If my acceptable level of error alpha is 1%, do I reject my null hypothesis? No, again, 1.2 is a bigger chance of being wrong than my acceptable level of error, which is alpha is equal to 1%. If I set that bar for myself at the beginning. And when do you set that bar? You set that bar before you even start the problem. You decide what's your acceptable level of alpha, right? And if you had said 0.05, you would have rejected the null hypothesis, right? That the salaries are the same, and you rejected it and accepted the alternative. Now, let's say that you can't reject it. Yes. Oh, the Z number is 5? Okay, thank you. Mea culpa. What can I tell you? You're right. Is it 5.4? It's 2,000. Was it 2,000 over? Yeah, okay, that's it. Okay, the Z value is 5. But you guys get the point, right? That would be a p-value of 0.00001 or something like that. It'd be very small. Okay, so the last point I want to make about this is that in some cases you may not be able to reject the null hypothesis. You may go through all of this, and the confidence intervals of these two things, the value of that other group is within the confidence interval of the sample that you have, the mean for the population of the sample that you have, or you may find that your level of alpha error, your z-score or your t-score, is not big enough to give you a p-value of less than 0.05. So you can't say with less than 5% chance of being wrong that the average salary is not 4,000. So you can't reject your null hypothesis. You haven't proved that the average salary is 4,000 or that they're the same. You just have failed to reject your null hypothesis. Okay? So what you would say in that case is, I failed to reject the null hypothesis. If you wind up with a p-value less than 0.05, I reject the null hypothesis, I accept the alternative hypothesis. If you don't wind up with a p-value less than 0.05, you say, I failed to reject the null hypothesis. You haven't proved the opposite. You've only failed to prove that they're different. Okay? So, welcome to real statistics. This is stuff that